Hey, what's up, guys? My name's Paul. I'm going to be behind the camera doing the narration. That guy up there, his name's Brendan. He's going to be doing the illustrations. And this is our fork system call tutorial. Let's do this. Okay, let's say we have a process, our program, that contains a couple of variables, a is equal to 1 and b is equal to 2. We will represent a process with a circle. Now, how would we identify this process? All active processes are uniquely identified by a PID or process identifier. For simplicity of our video, let's assign this process with a PID of 5. In your own program, you can use the system call getPID to find the PID for your own processes. When we call the fork system call on this process, it creates a new process called the child, which is a duplicate of the calling process that is now referred to as the parent. Now, when we say that the child is a duplicate, what we mean is that fork makes two identical copies of address spaces, one for the child and the other for the parent. Both processes are an exact copy of each other, except for their process identifiers and a few other minute details which don't really concern us. After a successful call to fork, both processes will start their execution at the next statement following the fork call. Now, the PID of the calling process is not important here. What is important is the integer each process returns. If the process returns 0, we know we're in the child. Else, if the process returns anything other than 0, we know we're in the parent. Now, at this point, both the parent process and the child process contain variables a is equal to 1 and b is equal to 2. After forking, it is unclear as to which process will run first, which is why we utilize the wait system call on the parent, to ensure that the child goes first. Using wait also ensures that the child terminates properly, preventing it from becoming a zombie. Now, we'll go into further details on this in a minute, so hang tight, guys, alright? Now, in our example, if we wanted to change our a and b to a is equal to 7 and b is equal to 8 temporarily, we would only do the changes to the child. After the variables are changed and used for whatever reason, we exit the child, resuming in the parent after the wait, where it is as if our variables were never changed at all. What happens in the child is only temporary and local to the child. Once we exit, those changes are gone. Now, we will not go into detail as to why you should be forking, but it is important to know that forking allows multiple processes to be handled independently from one another, meaning that what happens in one process will not affect the other. Now, remember what I said zombies a few minutes ago? What happens is that the wait system call actually frees up the resources that the child is using once the child state changes, i.e., when the child terminates. Without the wait call, although the child will still terminate, nothing will free up its resources, which may lead to memory issues. A child process that has terminated but still takes up resources as a result of not being waited on is referred to as a zombie process. Now, if your program is small enough and you're forgetting to wait on maybe a couple children, you're not really going to notice any negligible effects. But as your program becomes larger, you might have nested waits. Then the resource hogging can become more apparent. And it's generally bad practice. So don't forget to wait, guys. All right? And that's it.